Hello, everyone. Oh, good evening. My name is Gabriel Bornea. I'm a team lead in ING Hubs Romania. And today I'm going to talk to you about errors and why they are the forgotten part of your domain. So I've been writing backend and full stack applications for quite some time. Lately, I've been working with Kotlin and TypeScript, but I specifically enjoy Scala, which I write whenever I can. And more recently, Flix, which is very interesting to me. And I'm very enthusiastic about FP. So I've seen firsthand how poorly designed error handling leads to incidents and bugs that are lengthy, that are difficult to fix, and how those could have been prevented had we had a better error handling around them. So we're going to talk about the importance of error handling. We're going to see some techniques on how we can do that. We're going to see when accumulating errors is useful and important, how everything fits into what we call railway-oriented programming, and how this helps with maintainability, testability, composability, and so on. So most of the time, we tend to think about errors as an afterthought, so we don't give them the attention that we should. And this leads to a lot of nasty things, like unpredictable behavior, side effects, crashes, and sometimes even security vulnerabilities. Since this is a short presentation, we only have 30 minutes, I'm going to dive right into an example. Please keep in mind that this is an oversimplification of what processing a payment is, because it's not important the flow, it's important, the important things are the techniques that we apply to handle errors in a more efficient way. So this will start with a request to another system to get the user balance. We're going to check whether that user has sufficient funds. If so, we're going to move forward to actually initiate that payment. Then we're going to check whether the payment has been approved or not. If so, we return some confirmation, and this will end the flow. However, this is just the happy path, and we need to take into consideration that the application will fail. So first of all, what will happen if the user does not have sufficient funds? We want to return an error. Or if the payment is not approved for some reason, then again, we have to return an error. Now, in a conventional approach, we tend to use exceptions to handle errors, to throw them. Hopefully, someone will catch them and treat them. But this has some pitfalls, hidden side effects, and we tend to complicate the debugging, we tend to complicate the recovery just because the errors are handled in this way. Now the service that we're going to use today is a payment service, and at the first glance this might look okay, but however there are some fundamental issues with this code. The first one, if the balance is insufficient, we're throwing an error. Again, if the payment is not approved, we're throwing an error. But what's wrong with them? Well, first of all, the fact is that this is a generic error. It lacks any kind of context on what went wrong besides the message. And yeah, you can't do much with a message rather than log it or, I don't know, maybe show it to the user, but that's it. Moreover, there are two external services that we're calling. The balance client, which will give us back the balance, and the payment to initiate the actual payment. However, this has potential issues as well, because these are unhandled errors. So we're hoping that someone, someplace else, will take them into configuration. Now, if we treat errors as values, we can incorporate into our domain the logical errors, the ones that actually make sense to be in the domain, and we're not going to treat them as exceptional cases, because they're not. And this is important because now the handling is explicit. because usually we tend to wrap this inside some data type that is able to handle errors as well, like try, either, and so on. And today we're going to focus on two of those types. The first one is either, which basically represents a value that is made up of two possible types. On the left side, by convention, we tend to put the errors, and on the right side, we tend to put the success. So when we use an either, we either get, like the name says, an error, or the value that is the outcome of the computation. And the other one is the I/O, and even though they might look similar, they serve different purposes. I/O is useful when we want to wrap computations that might fail and also execute them lazily, defer their execution until we're actually going to need them. So if we take the first case where we check the user balance, instead of throwing the error, we're just going to return an either, and we put on the left side the same generic error. And we're going to do the same thing for the payment status verification. We put this on the left side of an either. And now, if we do this, the signature of our function will change, and instead of returning a string, which was the confirmation, now returning an either that contains the error or the string. And this has several benefits. The first one is that now everything is explicit. The function clearly communicates that it might fail. We gain improvements in testability because the outcome is explicit and we can cover all the branches. And because types like either and I/O have different combinators, they're very easy to combine one with another. So we've gained a pretty significant thing until now. We've made our errors explicit. However, we have two additional problems. We don't know which error occurred or why, and we lack the context to decide what to do next. And if we take the error and we try to think of the errors in terms of our domain, we're going to see that an error could mean a lot of things that make sense to us. Like, I don't know, there aren't sufficient funds, the currency was wrong, some fraud check failed, and so on. And these are basically types. And types, just like functions, have a very fundamental property, which is that they can be composed, which will become quite important for us in the next part of the presentation. Now, types are composed using something that we call sum types or algebraic data types, and an ADT can be one of several distinct variants, and the important thing is that each one can hold its own data. And this is important because it gives us context, not just the type of the error, the name of the error, it also has context on it, and we can act on that context. Now you're going to see this represented as union types, CIL types, and enums in many languages. Many languages are able to represent these kinds of types. But why use them? So, as I've said, it's important because each one is basically self-documented. It contains the context, and it makes it clear what can go wrong. The compiler now enforces that every variant is handled, so you don't get unhandled cases. Each error, as I've said, can carry its own data, which makes it, I would say, a bit more easy for us to make decisions on what to do next. And every time you add a new error or a new variant to an ADT, you're forced to basically update all the places where this is handled. And this is quite important because, again, you're not going to have unhandled cases. Of course, this requires some discipline, but it can be achieved quite easily. Now, I chose to represent, for this particular presentation, an ADT as a discriminated union, whereas you can see each of the error has something specific to it. Now, this is, again, simplified, but you can have obviously more context there which you can use in your applications. And now if we change our return type, it's more clear now. We know that this function will either fail with a payment error, and we know exactly what a payment error is because it's type safe, or it could succeed with some string. Now both these topics that we've discussed so far, the either type and ADT, work quite well in something that is called railway-oriented programming. And you can view railway-oriented programming as a railway that has two tracks. One is for the successful computation and the other one is for the failure path. And the key idea here is that each function returns either a success or a failure, and you can compose multiple functions regardless of their outcome. And if we look at our payment service again, we're going to see that this is a function that has some input and it produces an output, in this case an either. But this is made up of several steps. So the first one is getting the account balance, then checking the funds, then initiate the payment, and so on. So these are different steps that are required in order for our entire flow to be useful. And you can see this just as bricks of different shapes and forms that, when put together in the correct order, can be used to build larger flows, which in our case is the payment service. Now, if we were to look this on how it actually works, we have the balance client, and if it's successful, it would pass the result to the next function and so on until we reach the end. If not, if any error occurs, the computation is short-circuited. It will not invoke the next functions in the steps that we have, and it will carry the error to the last step. So this is what we basically mean about railway-oriented programming. Now, we achieved so far things like explicit type-safe error handling via ADTs, via either, and railway-oriented programming. However, this is fail-fast, but there are many cases in real world where you need to accumulate the errors. We want to capture multiple non-blocking issues that should execute in parallel, like, I don't know, multi-field validation, file import, or even complex workflows. So what we need to catch all the issues that may occur and put them together. And if we go back to our example, the one that we started where we got the balance, in the first place, we're not interested in getting the balance. We don't care the balance of the user. We care whether it has sufficient funds or not. But this is not the only thing that we might want to do here. We might want to check whether this payment is safe, or we might want to check whether the user has a daily limit that he doesn't want to go over it. And what we want to do is to execute everything in parallel. Now we don't care if there are sufficient funds, we care whether the validation has passed or not. So now, what actually happens when we execute all of this? Each function will return a box that contains either the error or the value that we're going to need later to do something with it. And we said that we want to capture everything and put them somewhere. In this case, we want to gather all the errors and throw them in this bag. We don't want to stop at the first issue that might happen. Moreover, we're also interested in the values, because we need the values to do something useful, hopefully, with them later. And now if we were to translate all of this into a code, it's going to look like this. We have the balance client that executes a request and returns either a payment error or some kind of In this case, it returns nothing. But either is not very well suited for these kinds of operations. And another better suited data type for this kinds of operation is the I/O, because it's capable, as I've said, of encapsulating operations that might fail, but also operations that we want to control when will actually be executed. Since we're using I/O, and I/O is asynchronous by nature, we don't need to wrap the result inside of a promise. It's enough to use the I/O. And we're going to do the same for the other two steps that we had previously with the limit check service and fraud service. Now we want to execute all of this in parallel. In order to execute this in parallel, we're going to use a common functional programming pattern that does exactly this. It captures every error that might happen inside of a list, inside of a data type, but also it merges all the results in a callback that we can use later. So now we have all operations executed in parallel. All the results are merged together. Each operation is executed. We're not stopping at the first one. All of them will be executed. And this has, I would say, two main benefits. The first one, it's good for us, engineers who write code, because we get a complete picture of what went wrong in one step, and we can potentially fix the issue where it lies, because we have a complete idea of what went wrong. But it's also important for the users, because now the users will get all the errors at once, and they will be able to fix everything in one go. And here maybe you can imagine a registration form where you put the username, the email, the password, and so on. You don't want the user to click and get, hey, your username is invalid. He fixes that, he clicks, hey, your email is invalid as well. With an approach like this, we can accumulate all of the errors at once, and we can give the user what went wrong in a single go. Now, as I've said in the beginning, applications fail. So when you write your code, always start with this in mind. The applications will always fail. It's not a matter of if, it's just when it will fail. And I found a very interesting report. Usually I don't look at these numbers, but I was curious for this presentation. And I saw that last year, nearly half of data center managers reported that they have at least one downtime for the data center. And when you translate this into cost, there were incidents that were like hundreds of thousands or even millions of dollars, which is extremely, which is a very high number. Since, again, this is a short presentation, we're going to look just at one major cause of issues, which is network instability. And this usually happens by timeouts, connectivity losses, unreachable service, and so on. And this can be handled to make the application more resilient by doing some steps. One of them would be understanding why and what went wrong and translate it into something that the domain can understand. We could choose to implement retries, timeouts based on the business needs that we have. We could implement things like fallbacks and circuit breakers. And we should always separate the concern. I mean, the domain should not be polluted by, I don't know, network errors. Now we're going to look at the limit service, which is an actual implementation. And so far we're doing a decent job. So we're logging if something went wrong, we're mapping it to something that the domain can understand, and so on. However, we should also attempt a retry based on some retry policy that we defined and that makes sense for us. Moreover, there are use cases where we might not want to block the flow in case a service is down, which may not be that important. So in this case, we could provide a default fallback that in case of a failure will allow the bigger flow to continue the execution. By using these concepts, we're also simplifying testing, because explicit error handling not only prevents hidden side effects, but it also makes the code easier to test, because we can test all the error variants, which ensures a full coverage. And when errors are just values, in the domain, you typically don't need any mocks or global error handlers and so on. And if we look at a test for the validation service that validates all of these three steps, we see that we don't need mocking or extra plumbing for the domain, because we can provide in-place implementations for those smaller functions. Now, because we have small independent functions that are composed together to build larger stuff, we can test those in isolation, or we can test everything together. And because every outcome is explicitly modeled, and because every possible failure is captured by the type system, we could do things like this. So for example, here we might want to test that the user has insufficient funds. And it becomes very easy to switch the successful response with an unsuccessful one. Or you could test multiple issues that might happen, for example, like we have here, insufficient funds and limit reached. And of course, you can inspect the list of errors, and you can do complex testing on this. Now, we're going to look at some principles. The first one would be that you should always treat errors explicit and composable, because it saves you a lot of time. Try to use typed constructs if possible. If not possible, there are also ways in which you can build a rich domain error. Try to use small functions that can be composed to build larger flows. Now, using errors as values has several benefits as well, because the code base becomes cleaner, easier to maintain, it's easier to debug, it's easier to test, and this is my favorite one, it eliminates hidden side effects. Your code becomes much more manageable. When starting with this, you should start small as always. You should integrate these techniques in small parts of your code base and grow from there. And try to use some existing tools. I think that nowadays every mainstream modern language has some sort of a tool or library that you can use to do these kinds of things. Now, if you want to read more, I have a list of articles and books that I enjoy, and I've read, I think, all of them here.